Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. For over 30 years, the Hubble Space Telescope has served as humanity's most trusted window into the cosmos. Launched in 1990, this remarkable instrument has fundamentally transformed our understanding of the universe, capturing images that have become iconic symbols of scientific discovery. From the breathtaking pillars of creation in the Eagle Nebula, to the deep field observations that revealed galaxies formed when the universe was merely a few 100 million years old, Hubble has consistently pushed the boundaries of what we thought possible. But as revolutionary as Hubble has been, astronomers and engineers are already envisioning its successor, not just an incremental improvement, but a quantum leap forward in our ability to peer into the deepest reaches of space and time. The concept of a megatelescope stationed at the second Lagrange point, or L2, represents the next evolutionary step in space-based astronomy, promising to unlock mysteries that even Hubble cannot touch. The James Webb Space Telescope, or JWST, already operating at L2 since 2021, has demonstrated the incredible advantages of this orbital position. Located approximately 1.5 million kilometers from Earth, L2 offers a gravitationally stable environment where spacecraft can maintain their position relative to both Earth and the Sun with minimal fuel consumption. This location provides an unobstructed view of the universe, free from Earth's atmospheric interference and the thermal noise that plagues ground-based observations. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The concept of a megatelescope builds upon these proven advantages while scaling up dramatically in both size and capability. Where Hubble's primary mirror measures 2.4 meters in diameter and Webb's segmented mirror spans 6.5 meters, a megatelescope could potentially feature mirrors measuring 20, 30, or even 50 meters across. Such massive apertures would collect exponentially more light, enabling observations of astronomical objects so distant and faint that they remain completely invisible to current instruments. The engineering challenges are staggering, but not insurmountable. Advanced materials, science has produced ultra-lightweight mirror segments that can be folded for launch and precisely deployed in space. Adaptive optics systems, originally developed to correct atmospheric distortion for ground-based telescopes, could be adapted to maintain perfect mirror alignment across enormous segmented arrays. Autonomous robotic systems could handle the delicate assembly and maintenance tasks required to keep such a complex instrument functioning optimally. The scientific potential is even more remarkable. A mega-telescope could directly image exoplanets orbiting nearby stars, analyzing their atmospheric compositions to search for biosignatures, chemical indicators of life. It could observe the formation of the very first stars and galaxies in the universe, peering back to an era when the cosmos was less than 100 million years old. It could map dark matter distribution on unprecedented scales, potentially revealing new physics beyond our current standard model. Perhaps most tantalizingly, such an instrument could begin to answer fundamental questions about our place in the universe. Are we alone? How did life emerge from the primordial chemistry of the early solar system? What lies beyond the observable universe's current boundaries? These questions have driven human curiosity for millennia, and a megatelescope at L2 could finally provide definitive answers. The road ahead involves overcoming tremendous technical, financial, and logistical challenges. International cooperation will be essential, as no single nation possesses the resources to undertake such an ambitious project alone. But the potential rewards, scientific, technological, and inspirational, justify the effort required to make this vision reality. To understand why the second Lagrange point represents the ideal location for humanity's next generation of space telescopes, we must first examine the elegant physics that makes this region of space so special. Lagrange points, named after the 18th century mathematician Joseph Louis Lagrange, are locations in space where the gravitational forces of two massive bodies, in this case Earth and the Sun, combine with the centrifugal force experienced by a smaller object to create regions of gravitational equilibrium. The Earth-Sun system contains 5 such points, designated L1 through L5. L1 sits between Earth and the Sun, approximately 1.5 million kilometers from Earth toward the Sun. L2 lies on the opposite side of Earth from the Sun, at the same distance but in the direction away from our star. L3 occupies a position on the far side of the Sun from Earth, while L4 and L5 form equilateral triangles with Earth and the Sun, leading and following Earth in its orbit by 60 degrees. Of these 5 locations, L2 offers unique advantages for astronomical observations. Unlike L1, which provides an excellent vantage point for solar observation but suffers from intense solar radiation, L2 allows spacecraft to maintain a constant orientation relative to both Earth and the Sun while remaining in Earth's shadow cone for significant portions of their orbit. This configuration provides natural thermal protection, reducing the complex thermal management requirements that would be necessary at other locations. The gravitational dynamics at L2 create a phenomenon known as a halo orbit, a large, stable, orbital path that spacecraft can follow around the Lagrange point itself. These halo orbits typically extend several 100,000 kilometers from the theoretical L2 point, providing spacecraft with flexibility in positioning while maintaining the gravitational advantages of the location. The JWST currently follows such a halo orbit, completing one full orbit around L2 approximately every 6 months. For a megatelescope, these orbital characteristics translate into several crucial advantages. First, the gravitational stability means that station-keeping maneuvers require minimal fuel, allowing mission planners to focus propellant budgets on precision pointing and occasional orbital adjustments rather than constant position maintenance. This efficiency is particularly important for missions designed to operate for decades rather than years. Second, the thermal environment at L2 is remarkably stable and predictable. The Sun provides a constant energy source for solar panels, while the spacecraft's instruments can be shielded from solar radiation using relatively simple sun shields. This thermal stability is essential for the ultra-precise measurements that modern astronomy demands, as temperature fluctuations can cause minute changes in mirror shapes and instrument calibrations that would compromise observational accuracy. SAFIFI communication advantages of L2 are equally significant. Unlike satellites in low Earth orbit, which pass in and out of contact with ground stations, spacecraft at L2 maintain continuous communication with Earth through the Deep Space Network, a key system of large radio antennas located in California, Spain, and Australia. This constant connectivity enables real-time mission control, rapid data transmission, and immediate response to unexpected events or opportunities. Perhaps most importantly for a megatelescope, L2 provides an unobstructed view of the entire celestial sphere, with the exception of a small region blocked by the Sun. This 360-degree visibility allows astronomers to observe any target in the sky without the geometric constraints that affect Earth-orbiting telescopes, which must work around Earth's shadow and avoid pointing toward the Sun. The journey to L2 also presents manageable challenges for large spacecraft. The trajectory requires approximately 3 months of travel time, during which spacecraft systems can be gradually activated and tested. This extended commissioning period has proven invaluable for complex missions like Webb, allowing engineers to identify and resolve minor issues before beginning full scientific operations. For a megatelescope potentially measuring tens of meters across, L2's combination of gravitational stability, thermal predictability, communication reliability, and observational flexibility makes it the only practical location for such an ambitious instrument. The physics of this remarkable point in space provides the foundation upon which humanity's grandest astronomical dreams can be built. The engineering challenges involved in constructing a mega-telescope for L2 deployment push the boundaries of human technological capability in ways that would have seemed impossible just decades ago. Creating a space-based telescope with a primary mirror 50 meters in diameter, roughly the size of a football field, requires revolutionary advances in materials, science, precision manufacturing, and autonomous assembly systems. The primary mirror represents the most formidable engineering challenge. Traditional telescope mirrors, like those used in Hubble or ground-based observatories, are typically made from solid glass or ceramic materials that provide excellent optical properties but are prohibitively heavy for space applications. A 50-meter solid mirror would weigh thousands of tons, making launch completely impractical with any conceivable rocket system. The solution lies in segmented mirror technology, already demonstrated successfully by the JWST and ground-based telescopes like the 30-meter telescope, currently under construction. A megatelescope would employ hundreds or potentially thousands of individual mirror segments, each precisely manufactured and controlled to function as components of a single, coherent optical system. These segments would be manufactured from ultra-lightweight materials such as beryllium, silicon carbide, or advanced composite materials that maintain their shape across the extreme temperature variations of space. Each mirror segment must be controlled with nanometer-level precision, accuracies comparable to positioning an object the thickness of a human hair to within the width of an atom. This requires sophisticated actuator systems capable of making minute adjustments to each segment's position and orientation in response to thermal changes, gravitational forces, and mechanical stresses. The JWST's 18 mirror segments each incorporate 6 degrees of freedom adjustment, but a megatelescope might require even more sophisticated control systems to maintain optical coherence across its vastly larger surface area. The deployment mechanism presents equally daunting challenges. The telescope must be folded into a configuration compact enough to fit within a launch vehicle's payload fairing, then unfold with perfect precision once in space. This process, known as deployment, has been compared to complex origami, but the analogy understates the engineering precision required. Every hinge, actuator, and structural element must function flawlessly, after months in the harsh environment of space, with no possibility of hands-on maintenance or repair. Recent advances in shape memory alloys and smart materials offer promising solutions to some deployment challenges. These materials can be programmed to assume specific configurations when heated or subjected to electrical currents, potentially enabling self-deploying structures that require minimal active control systems. Carbon fiber composites and advanced polymers provide exceptional strength-to-weight ratios while maintaining dimensional stability across wide temperature ranges. The structural engineering challenges extend beyond the primary mirror to the entire telescope assembly. A megatelescope must maintain its structural integrity while pointing to different regions of the sky, requiring a support structure that is simultaneously lightweight, rigid, and dynamically stable. The natural frequency of structural vibrations must be carefully designed to avoid interference with the telescope's precision pointing systems and scientific instruments. Thermal management becomes increasingly complex as telescope size increases. Temperature differences of even a few degrees across the telescope's structure can cause dimensional changes that destroy optical alignment. Multi-layer insulation, radiative cooling systems, and active thermal control systems must work in concert to maintain uniform temperatures across the entire instrument. Perhaps most remarkably, much of this complex assembly process must occur autonomously in space, guided by sophisticated robotics and artificial intelligence systems. Ground-based mission control can provide overall supervision, but the 3-second communication delay to L2 means that real-time human control of deployment operations is impossible. The telescope must essentially build itself, following pre-programmed sequences while monitoring its own assembly progress and making adjustments as needed. These engineering challenges, while daunting, are not insurmountable. Each represents an evolution of technologies already demonstrated in space missions, ground-based telescopes, and terrestrial engineering applications. The convergence of these technologies in a single, integrated system would represent one of humanity's greatest engineering achievements, comparable to the Apollo program or the International Space Station in scope and ambition. The scientific capabilities of a 50-meter megatelescope at L2 would revolutionize astronomy, in ways that fundamentally transform our understanding of the universe and our place within it. The relationship between telescope aperture and observational capability follows well-established physical principles, but the implications of scaling up to megatelescope dimensions are profound and far-reaching. Light-gathering power increases with the square of a telescope's diameter, meaning a 50-meter telescope would collect nearly 400 times more light than Hubble's 2.4-meter mirror, and over 50 times more than the JWST's 6.5-meter aperture. This dramatic increase in sensitivity would enable observations of astronomical objects so faint that they remain completely invisible to current instruments, effectively extending the observable universe's boundaries and allowing astronomers to study cosmic phenomena in unprecedented detail. Angular resolution, the ability to distinguish fine details in astronomical images, improves linearly with telescope diameter. A 50-meter telescope would achieve angular resolutions of approximately 4 milliseconds at visible wavelengths, roughly 50 times better than ground-based telescopes and 20 times superior to Hubble. This resolution would enable direct imaging of exoplanets orbiting nearby stars, a capability that remains beyond current technological reach for all but the largest and most unusual exoplanetary systems. The implications for exoplanet science are staggering. Current exoplanet detection methods rely primarily on indirect techniques such as transit photometry and radial velocity measurements, which can detect planets but provide limited information about their physical characteristics. Direct imaging, with a megatelescope, would enable spectroscopic analysis of exoplanetary atmospheres, potentially revealing the presence of water vapor, oxygen, methane, and other molecules that could indicate biological activity. The search for biosignatures, chemical indicators of life, represents one of the most compelling scientific applications for a megatelescope. On Earth, the presence of atmospheric oxygen combined with water vapor and ozone creates a distinctive spectroscopic signature that would be detectable from interstellar distances. A megatelescope could search for similar signatures around nearby stars, potentially providing the first definitive evidence of life beyond our solar system. Early universe observations would benefit equally dramatically from a megatelescope's capabilities. The most distant galaxies currently observable formed when the universe was less than 400 million years old, during an epoch known as the Cosmic Dawn. A megatelescope could push these observations back to even earlier times, potentially. Observing the formation of the very first stars and galaxies when the universe was only 100 million years old. These earliest cosmic structures formed from primordial hydrogen and helium created during Big Bang nucleosynthesis before heavier elements were forged in stellar cores. Observing these population 3 stars, the first generation of stars in the universe, would provide crucial insights into the processes that ended the cosmic dark ages and began the complex chemistry that eventually led to planet formation and life. Dark matter mapping represents another frontier where megatelescope capabilities would prove transformative. While dark matter cannot be observed directly, its gravitational effects on visible matter create subtle distortions in the shapes of distant galaxies, a phenomenon known as weak gravitational lensing. A megatelescope could map these distortions with unprecedented precision, creating detailed 3-dimensional maps of dark matter distribution throughout the universe. Such maps could reveal whether dark matter's properties match current theoretical predictions or whether new physics beyond the standard model is required to explain its behavior. The distribution of dark matter on cosmic scales encodes information about the universe's fundamental properties, including the nature of dark energy and the validity of general relativity on cosmic scales. Time domain astronomy, the study of astronomical objects that change over time, would also benefit enormously from megatelescope capabilities. The instrument could monitor thousands of exoplanets simultaneously, tracking atmospheric changes, weather patterns, and seasonal variations. It could observe stellar explosions, black hole mergers, and other transient phenomena with sensitivity and temporal resolution impossible with current instruments. Perhaps most significantly, a megatelescope would possess the sensitivity to detect entirely new classes of astronomical objects and phenomena that remain undiscovered simply because they are too faint or too small to observe with current instruments. History suggests that major advances in observational capability invariably lead to unexpected discoveries that reshape our understanding of the universe in ways that cannot be predicted in advance. The construction and operation of a L2 megatelescope would require unprecedented levels of international cooperation and financial commitment, dwarfing even the most ambitious space science projects undertaken to date. The James Webb Space Telescope, with its total development cost of approximately $10 billion, provides a useful benchmark for understanding the scale of resources required, but a 50-meter megatelescope would likely cost several times that amount, potentially reaching $50 to $100 billion over its complete development life cycle. No single nation possesses the financial resources, technical expertise, and industrial capacity necessary to undertake such a project independently. The European Space Agency's partnership with NASA on the JWST, where ESA contributed launch services and key instruments while NASA provided overall project leadership, demonstrates how international collaboration can successfully manage complex space science missions. However, a megatelescope would require cooperation on an entirely different scale, potentially involving space agencies from the United States, Europe, Japan, Canada, China, India, and other spacefaring nations. The International Space Station provides another model for large-scale space cooperation, bringing together 15 nations in a sustained partnership that has operated continuously for over 2 decades. The ISS partnership demonstrates that nations can successfully collaborate on complex long-duration space projects despite political tensions and changing geopolitical circumstances. However, the megatelescope project would face additional challenges, as scientific priorities and technical approaches might vary significantly among participating nations. Funding models for such an ambitious project would likely need to evolve beyond traditional government space budgets. Public-private partnerships, similar to those being developed for commercial space exploration, could provide additional resources and technical expertise. Private foundations and philanthropic organizations focused on fundamental science research might contribute significant funding, as they have for ground-based telescope projects like the 30-meter telescope and the Giant Magellan telescope. The timeline for developing a megatelescope would span multiple decades, requiring sustained political and financial commitment across several electoral cycles in participating democracies. The JWST took approximately 25 years from initial concept to first science operations, and a megatelescope would likely require even longer development periods due to its increased complexity and the need for fundamental technology. Technology readiness represents a critical factor in project timeline planning. While many of the technologies required for a megatelescope exist in prototype or demonstration form, achieving the reliability and precision required for space deployment would require extensive testing and refinement. Advanced materials, precision, actuators, autonomous assembly systems, and ultra-stable structural designs would all need to mature significantly before integration into a flight system. Risk mitigation strategies would be essential for maintaining international support throughout the development process. The cost overruns and schedule delays that affected the JWST project, while ultimately acceptable, given the mission's spectacular success, would be much more problematic for a project costing 10 times as much. Rigorous systems engineering, extensive ground testing, and conservative technical approaches would be necessary to maintain stakeholder confidence. The scientific return on investment for a megatelescope would be enormous, but communicating this value to policymakers and the public would require sustained outreach efforts. The dramatic images and discoveries from Hubble and Webb have helped maintain public support for space science, but a megatelescope project would need to articulate its scientific goals in terms that resonate with broader societal interests, such as the search for life beyond Earth and understanding humanity's cosmic origins. Industrial benefits could provide additional justification for the massive investment required. Large space projects historically drive technological innovation that finds applications in other sectors, from materials science to precision manufacturing to autonomous systems. The technologies developed for a megatelescope could contribute to advances in renewable energy, advanced manufacturing, robotics, and artificial intelligence. Educational and inspirational benefits represent another important consideration. Major. Space projects capture public imagination and inspire young people to pursue careers in science, technology, engineering, and mathematics. The Apollo program's impact on STEM education in the 1960s and 70s demonstrates how ambitious space projects can influence entire generations of students and researchers. Managing such a complex international project would require new forms of governance and decision-making structures. Traditional space agency hierarchies might need to evolve to accommodate the diverse interests and technical approaches of multiple participating nations. Clear agreements on intellectual property, data sharing, and scientific credit would be essential for maintaining partnership cohesion throughout the project's development and operational phases. The path toward a 50-meter megatelescope at L2 cannot be achieved through a single technological leap, but must follow a carefully planned sequence of increasingly ambitious precursor missions that demonstrate and refine the critical technologies required for such an unprecedented undertaking. This incremental approach reduces technical risk, provides valuable operational experience, and maintains political and financial support by delivering scientific results throughout the development process. The logical progression begins with ground-based technology demonstrations that validate key concepts under controlled conditions. The James Webb Space Telescope's mirror deployment mechanism was extensively tested on Earth using specialized facilities that simulate the space environment, including thermal vacuum chambers and precision alignment systems. Similarly, megatelescope technologies would require extensive terrestrial testing before space deployment, potentially including full-scale prototype sections that demonstrate segmented mirror control and autonomous assembly processes. Near-term, precursor missions could focus on demonstrating specific technologies essential for megatelescope success. A technology demonstration mission might deploy a modest array of interconnected mirror segments in low Earth orbit, validating precision, alignment systems and autonomous assembly procedures under actual space conditions. Such missions could use CubeSat or SmallSat platforms to reduce costs while providing valuable engineering data. Formation flying represents another critical technology requiring space demonstration. A megatelescope might eventually consist of multiple separate spacecraft flying in precise formation, with some components serving as mirror segments, while others house scientific instruments or provide structural support. The European Space Agency's Proba 3 mission, scheduled for launch in 2024, will demonstrate precision formation flying techniques that could be scaled up for larger astronomical applications. Robotic assembly in space represents perhaps the most challenging technology requiring development. While the International Space Station has demonstrated that complex assembly operations can be performed in space using both human astronauts and robotic systems, a megatelescope would require fully autonomous assembly with unprecedented precision requirements. Robotic demonstration missions could validate assembly procedures, test autonomous decision-making systems, and develop the specialized tools and interfaces required for space-based telescope construction. Intermediate-scale telescope missions could bridge the gap between current capabilities and ultimate megatelescope goals. A 15-meter telescope deployed at L2 would be significantly larger than current space telescopes, while remaining within the realm of demonstrated technology. Such an instrument would provide transformative scientific capabilities while serving as a pathfinder for even larger systems. The experience gained from operating a 15-meter space telescope would be invaluable for planning megatelescope operations. Advanced materials development represents another area where incremental progress is essential. Ultra-lightweight mirror, materials, deployable structural elements, and precision actuator systems All require extensive development and testing before incorporation into flight hardware. Partnerships with aerospace industry and materials science research institutions could accelerate this development process while ensuring that new materials meet the stringent requirements of space applications. Artificial intelligence and autonomous systems development would proceed in parallel with hardware development. A megatelescope would require sophisticated AI systems capable of autonomous assembly, precision alignment, fault detection and recovery, and adaptive observation planning. These systems could be developed and tested through progressively more complex missions, beginning with simple automated functions and evolving toward full autonomous operation. Ground-based extremely large telescopes currently under construction provide valuable test beds for many megatelescope technologies. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope all incorporate segmented mirror systems, adaptive optics, and precision control systems that are directly relevant to space applications. Collaboration between ground-based and space-based telescope projects could accelerate technology development while reducing duplicated effort. International coordination of precursor missions would be essential for maximizing technological progress while minimizing costs. Different nations and space agencies could focus on developing specific technologies or components, sharing results through established international cooperation frameworks. This approach would distribute development costs while ensuring that all participating entities gain valuable experience with megatelescope technologies. The timeline for precursor missions would likely span 2 to 3 decades, with increasingly sophisticated demonstrations leading toward a full megatelescope capability. Early missions might focus on fundamental technologies such as precision pointing and mirror segment control. Mid-term missions could demonstrate formation flying and robotic assembly. Later precursor missions might deploy substantial telescope arrays that provide significant scientific capabilities while validating technologies for even larger systems. Success metrics for precursor missions would need to balance technological demonstration goals with scientific productivity. Each mission should contribute meaningfully to astronomical knowledge, while advancing the technologies required for ultimate megatelescope success. This dual focus would help maintain public and political support throughout the extended development period, while ensuring steady progress toward the ultimate goal. The deployment of a megatelescope at L2 would mark more than just a technological achievement. It would represent a fundamental threshold in humanity's relationship with the cosmos, potentially providing answers to questions that have shaped philosophical and scientific thought for millennia. The instrument's unprecedented capabilities would not merely extend our current understanding, but could fundamentally transform how we perceive our place in the vast expanse of space and time. The search for life beyond Earth stands as perhaps the most profound scientific quest enabled by megatelescope technology. For the first time in human history, we would possess the capability to systematically survey nearby star systems for planets, harboring the chemical signatures of biological activity. The detection of biosignatures, atmospheric compositions indicating the presence of life, around even a single exoplanet, would revolutionize biology, philosophy, and our understanding of life's cosmic significance. Consider the implications of discovering that life exists on multiple worlds within our local galactic neighborhood. Such a finding would suggest that life is not a rare cosmic accident, but rather a natural consequence of planetary evolution under appropriate conditions. This discovery would fundamentally alter our perspective on Earth's uniqueness and raise profound questions about the diversity of life forms that might exist throughout the galaxy. Conversely, if intensive searches reveal that Earth appears to be unique among hundreds of surveyed planetary systems, this finding would carry equally profound implications. The apparent rarity of life would suggest that our planet occupies an extraordinary position in cosmic history, carrying unique responsibilities as potentially the only known repository of consciousness and complex life in our region of the galaxy. The megatelescope's ability to peer deeper into cosmic history than ever before would provide unprecedented insights into the universe's evolution and ultimate fate. Observations of the first stars and galaxies would reveal how the cosmos transitioned from the simple hydrogen and helium created during the Big Bang to the complex chemical diversity that enables planet formation and life. These observations would test fundamental theories about cosmic evolution and potentially reveal new physics governing the universe's earliest epochs. Dark matter mapping capabilities would address one of the most significant mysteries in modern physics. The megatelescope's precision measurements of gravitational lensing effects could determine whether dark matter's properties match theoretical predictions or whether entirely new physics is required to explain cosmic structure formation. Such discoveries could lead to revolutionary advances in our understanding of space, time, and matter itself. The instrument's time-domain capabilities would transform our understanding of cosmic processes by revealing how astronomical objects change and evolve over timescales ranging from hours to years. Monitoring thousands of exoplanets simultaneously would provide insights into planetary atmospheres, weather patterns, and potentially even seasonal changes on worlds orbiting distant stars. These observations could reveal the dynamic nature of planetary systems and help identify worlds most likely to harbor stable conditions for life. Perhaps most significantly, a megatelescope would establish humanity as a truly spacefaring civilization capable of undertaking projects that span multiple generations and require unprecedented levels of international cooperation. The technological and organizational capabilities required to construct and operate such an instrument would position humanity for even more ambitious endeavors, potentially including interstellar exploration missions and the establishment of permanent human presence throughout the solar system. The educational and inspirational impact of megatelescope discoveries would influence generations of scientists, engineers, and explorers. Just as Hubble's images have inspired countless students to pursue careers in science and technology, the megatelescope's revelations about exoplanets, early universe structure, and cosmic evolution would motivate young people worldwide to tackle the fundamental questions about our cosmic origins and destiny. The project would also demonstrate humanity's capacity to undertake endeavors that transcend national boundaries and political differences. The level of international cooperation required would establish precedents for addressing global challenges, such as climate change, resource management, and sustainable development. The technological innovations developed for the megatelescope would find applications in renewable energy, precision manufacturing, autonomous systems, and space exploration. Looking toward the future, a successful megatelescope mission would likely inspire even more ambitious projects, potentially including multiple megatelescopes working in concert as an interferometric array or specialized instruments designed for specific scientific goals such as direct exoplanet characterization or gravitational wave detection. The megatelescope would mark the beginning of a new era in which humanity routinely undertakes projects on cosmic scales. Ultimately, the megatelescope represents more than a scientific instrument. It embodies humanity's deepest aspirations to understand our place in the universe and our potential role in cosmic evolution. By extending our vision to encompass potentially habitable worlds around distant stars and the earliest epochs of cosmic history, this remarkable instrument would help answer the ancient question of whether we are alone in the universe while simultaneously inspiring us to become worthy of whatever cosmic destiny awaits our species among the stars.